Hello, and thank you for your interest in this e-talk. I will be speaking about the information content of galaxy spectra, and in this case, given that this symposium is dealing with machine learning, we are looking at this problem at a very fundamental level in the sense of saying how much information can be extracted with any method whatsoever, any type of sophisticated machine learning algorithm. So in this case, we'll be looking into the aspect of entropy. Here is my list of collaborators, and let's go. The astrophysical context is as follows. When we observe spectra, especially in the near ultraviolet, optical, and near infrared window, what we get is this continuum along with absorption lines from the atmospheres of stars, covering a wide range of stellar mass composition. For instance, these are the models from Bruchsal and Charlot for solar metallicity in red, lower metallicity in blue, as a function of age, as you can see here in the animation. So the standard way to proceed with this, you basically take the observation of a galaxy, you take the spectrum, and then you compare with population synthesis models to try to derive things like the star formation history, chemical enrichment history, etc. And you can use all sorts of comparisons using a likelihood approach, chi-squared fitting methods, etc. An alternative approach is to say, well, we are not going to depend on the models at all. Perhaps we'll be using them a posteriori, but initially we consider this to be a blind source separation problem. Namely, a galaxy is made up of a number of stellar populations that are mixed, and we need to unmix them without knowing the original mixture. So this is the typical way that methods such as PCA, ICA, etc. proceed. The machine learning algorithms also can be used. Convolutional neural networks, for instance, can be trained supervising a number of spectra for which we already know what's going on, perhaps using simulations, or perhaps not. Or you can even go for a full unsupervised approach using machine learning. But the bottom line is that all these methods will ultimately depend on the amount of information encoded in the spectra. I mean, all these machine learning algorithms in a blind way are looking into variations in the spectra, so we need to understand properly how much of that variation is present, and that leads us to the concept of entropy. The entropy of spectra can be defined if we alternatively to the standard definition of the spectrum of a galaxy as the flux or the amount of photons as a given wavelength, we produce this photon counter interpretation. We simply use our spectrograph as a photon counter, and every time we detect a photon, we ask ourselves, what is the probability that that photon will have a wavelength lambda? So directly you get this P of lambda probability from which you derive the entropy using information theory. Remember, the entropy is a measure of surprise that you have, basically from having a distribution for which you know already that the photon will always have the same wavelength, like let's say in a laser beam, or white light, where you never know what wavelength the photon will have. So these two regions will have extreme values of entropy. For a given spectrum, as you see from this expression, the entropy is just a single number, which perhaps it's not too useful. So the way we did it was to define this number, this h, within a wavelength interval, and then we move this interval. So the choice here, there could be a single talk on justifying this approach, but in principle for the spectra of galaxies at the typical resolutions that we have, this window of 100 angstrom is optimal. So then automatically we have a function h of lambda within that delta lambda, that is our entropy spectrum, and we can define the complementary, so one minus that one, this one corresponding, one meaning basically the maximum entropy, automatically that gives you the amount of information content. So this is our way to proceed. So these are the entropy spectra that we get for a set of simple stellar population models from Bruchsal and Charlot as a function of age, as you see here. And here you see wavelength, and automatically you can appreciate that the entropy is only present, significant levels of negentropy of information is only present in very specific windows of my spectrum. Here I'm running in my wavelength within this window delta lambda. I'm not specifically choosing these regions. So you can see, for instance, here or here, the entropy variations are minimal. There's not much going on. Even though there are a number of lines, the variations are not so strong. Especially in the D4000, the 4000 angstrom break region, we found substantial variations. Balmer absorption as well, the magnesium iron region, the sodium absorption region, etc. We find variations. So these could be the regions where we can target our values of entropy. It is also interesting and, of course, unsurprising to see that the standard approach, we were using indices such as the Lick system that were specifically in the regions where the entropy variations are largest. This is just another way of showing the same result. Now the negentropy is shown as a grayscale here as a function of wavelength and age, and once more you see that only in those regions is where you find most of the variation. And I also would like to show you the issue that there are substantial correlations that I will talk about at the end of this talk. Additional factors that we have to keep an eye out on, especially because we're dealing with observational data, signal to noise. Of course, the signal-to-noise ratio will affect the probability distribution and hence the entropy. So if you have very noisy data, the data will become more blurred, which means that the amount of entropy will be higher. There's less information in a way. So if you're comparing samples with a wide range of signal-to-noise ratios, then entropy will be a signal picked up in terms of signal-to-noise, and entropy will be connected. And this is something that we have to be aware of. There's a figure at the end of this talk that I will show you regarding this. Spectral resolution is also important, not only the instrumental resolution of the spectrograph, but also the velocity dispersion of the galaxy. So if you're observing a massive galaxy, your velocity dispersion will be larger, and that means the photons will be more blurred. The entropy will also change accordingly, so the amount of information will vary. For instance, here you see this is from a simulation at 10 gigayears. This is for signal-to-noise ratio 5, and this is for 300 kilometers a second. You see, if you consider a massive galaxy, 300 kilometers a second, the amount of information drops by a factor of 1/2. So a totally blind machine learning algorithm will quickly pick up on those, so we have to be very careful about these types of processes. If we apply the same type of analysis to Sloan classic single fiber spectrograph data, then you see this figure. This has been separated into quiescent star forming in AGN using the nebular emission classification of the standard VPT diagram. And you can see once more that we get same results. I mean, just in this figure you can see them side to side, the simple stellar population models and the Sloan spectra. You have typical similar types of variation in 4000, H-band, G-band, and H-gamma, etc. And then you also have the incorporated effect of emission lines. For instance, oxygen 3 especially prominent in the AGN spectra, H-alpha especially in star-forming galaxies, etc. That's why these things usually will be removed, mainly because the origin of those emission lines are coming from the gaseous component, which are independent to the stellar populations. So now what we do is apply principal component analysis to our systems. But now what we're going to be doing is, rather than using the whole PCA on the whole entropy spectrum, because we already know that there are these specific windows, we're going to be concentrating on them. So we define the D4000 region, the H delta, H gamma, magnesium B, iron, and sodium. So 1, 2, 3, 4, 5, 6, 6 numbers for each spectrum, and then we apply principal component analysis. And these are the eigenvalues corresponding to our entropy approach that I have just described, and we have the line strength analysis, which is a traditional thing. You measure those indices in the good old-fashioned way, and then you apply PCA. And these are the weights. The colors correspond to positive or negative number. It doesn't really matter that much what we have here. The size of the symbol corresponds to the amount, if you wanted, the weight given to one of those for principal component 1, 2, and 3, using either the line strength analysis or the entropy analysis. And well, let's just go one step here. In this table, we automatically see that if you do the line strength analysis, you need to go up to 4 principal components to encapsulate 95% of variance. And let's make the interpretation of variance as information. In entropy, only 2 components are actually encoding this amount of information. You see here the distribution. This is the spectra on PC1 versus PC2 space for line strength and negentropy analysis. And you see that they are more or less comparable. The star-forming, AGN, and quiescent separate, live in different portions of our diagram. Going back one slide, you see the weights associated, especially on the entropy, because that's the one that encapsulates in just a couple of components, encapsulates a huge amount of variance. You see the first one is the D4000, the second is H delta. If you go to the third component, then you get a combination of H delta, H gamma, and perhaps sodium. So it's also interesting to see that we have not applied any models, we have not applied any pre-knowledge from previous papers at all, we just use the information content. We end up saying that the most important aspects of a spectrum would be the 4000 break and H delta, which is an approach done by traditional papers that you have seen many times in the literature. So the next step is then say, okay, now what happens if I compare, let's say for a given sample, the two extreme values of PC1 or of PC1 for star-forming AGN and quiescent galaxies. So you take all those galaxies at the 5th percentile and the 95th percentile in the three classifications, and what we find is this type of figure. So the 5th percentile is shown in blue, the 95th percentile is shown in brown, and then you can see the distribution separately for star-forming, quiescent, and AGN, for the indicators we use, 4000, H delta, etc., and also for a number of variables that we already, observables. We have velocity dispersion, stellar mass, redshift, and signal-to-noise ratio. So you see that first of all, if you use these types of information, you find, as expected, as we already know, 4000 break is quite important. Magnesium B is also quite significant. And then up to some level, the sodium deabsorption is also important. In terms of velocity dispersion, there's not so much of a variation. Also, I note that this sample by construction has been restricted quite substantially in velocity dispersion to reduce huge amounts of variations from low mass to high mass galaxies. Stellar mass, not much of a variation, and redshift, which is good news. There's no bias or no systematic. But notice here that for the star-forming galaxies, signal-to-noise ratio doesn't play a big role, but for quiescent and AGN, there is a substantial difference. So PC1 is also picking a signal from the signal-to-noise ratio. So we have to be very careful, because if we use this on a blind method with, let's say, a very sophisticated convolutional neural network, perhaps the signal we will be picking would be just a signal-to-noise. So that's something that has to be taken with some caution. So just to finish here very quickly, before the conclusions, I just wanted to show what happens if I apply to the models the covariance of the different indicators we have used, where we have most of the entropy, 4000, H delta, H gamma, etc. The covariance normalized to unit variance, you can see the enormous level of correlatedness. You can see that D4000 with respect to H gamma, the amount of correlation is really huge. The lowest values that you have are still quite high, which means automatically that even though you're dealing now with 6 numbers, 1, 2, 3, 4, 5, 6, you actually have far fewer degrees of freedom. And this also applies to all this analysis where you do spectral fitting. You have to be very careful. You may have many flux, if you want, units, but the correlation is so high, the effective number of free, if you want, independent indicators is relatively small. And this is why it is so tremendously difficult to extract detailed information from spectra to derive stellar populations. So in this final slide, I conclude with the idea that galaxy spectra, and here I'm focusing on the near ultraviolet, optical, and near infrared part of the spectral window, encode tremendously valuable information regarding the underlying stellar populations, the content in terms of age distribution, chemical enrichment distribution, the kinematics, etc. So this is very important, and we already know that we have a well-defined problem regarding various age metallicity degeneracies, let's put it that way, or even more complicated ones. Now there is one more step in the machine learning era to try to extract that information in a different way to the traditional approach, which is based simply on comparison with population synthesis models. So we need to be aware of the actual information that any method can extract. This talk is, as you can imagine, we are going beyond the standard approach that everybody is working on in this field. It's basically trying to say how much information, how much variation is encoded here. So information in the sense of entropy, it shows basically a limited set of interesting spectral windows. This is already well known. We talked about the leak indices, etc. But this is shown at a very fundamental level, that if you see the variations in the spectra, only very specific regions are showing you the types of variations that, for instance, a machine learning algorithm will pick up. So can machine learning do better than the traditional approach? And this is the big question that we have there. I also showed this slide with the high level of correlatedness that you have among different flux levels at all different wavelengths, which automatically means that the real number of degrees of freedom that we have in the system is substantially lower than what one would expect from the sheer number of flux values. So I finished with that one. We have a paper already in the system, and we will be posting this in the archive very soon, as you can see there. In any case, if you're interested in this paper and any other things related to the material that I have been presenting today, I would be very happy if you get in touch with me at this email address. So, well, take care and enjoy the symposium.